I'm going to talk about societal scale cyber-physical systems and what we're calling the emerging data market. So this idea of a data market has been in existence for a while in other areas, but we're starting to see this come about in large-scale infrastructure systems. So we're interested in taking a look at how we can model this. Roy alluded to this in his talk, so I hope that I can make some connections to the things that he talked about. Usually we give this as a tag team talk, so this will be a different version of this. Yeah, so this is a joint work with a lot of different people. These people have individually worked on some of the projects, but not necessarily all of them. Yeah. Okay. So I'll just start with something I guess we all know. Urban centers are expanding, and there's a lot of usage of Internet of Things types devices. So almost everybody now has a smartphone. And so what's happening is that infrastructure systems are coming to an important inflection point. So we're seeing new sensing modalities that allow us to extract interesting analytics. We're seeing these IoT platforms that are allowing us to close the loop around the end user. And in addition, we're seeing third-party companies emerge and enter this market, making up for services that traditional service providers can't provide. So what this means is two things. One, the existing infrastructure is being stressed. And two, it's increasingly becoming more smart and connected. So one of the things that we're seeing in particular is the use of new things like smart meters and other smart sensors that allow us to build user models that can then help us improve our operational decision making. And so I'd like to just touch on a couple things that we've been working on, one in the area of energy and one in the area of transportation. So my talk will continue in this fashion. So I'm going to try to build up an abstraction of what we're calling the data market by introducing the different market participants slowly as we go through, and I will give examples of work that we're doing both in the energy space and the transportation space. So the first one, which I was hoping Roy would talk a little bit more about, but it's basically the motivation for why we got started thinking about privacy. So we started looking at this problem of taking whole home energy signals and decomposing it into device level usage to be able to do things like improve load forecasting and build better economic models. What we quickly realized was that by breaking up the whole home energy signal into device level pieces, you could infer quite a bit about individuals. Okay, so switching gears to the transportation space, one of the projects I'm currently working on with the Seattle Department of Transportation is looking at urban parking. So we're taking a bunch of data that they have on parking transactions for the last 4 years, and other factors or other data such as land use, economic indicators like fuel price, things like that. And we're trying to pass this into a learning framework in which we can try to understand different aspects of the system, such as verify ways in which they do pricing. So one of the things that we looked at is how to cluster based on a set of features, including arrival rates, the geographic location, and histograms of parking durations to figure out what are the more natural neighborhood boundaries that can be used for parking. So the way that Seattle does it now is that they just say, okay, well, we're going to take the existing neighborhood boundaries that have just been known for a long time, maybe due to geography or whatever other reason, and we're going to do pricing based on those neighborhood boundaries. But maybe it's more intuitive to do pricing, or more effective perhaps to do pricing based on boundaries that are extracted out of the data itself. So one of the interesting things you see when you do this is that some existing neighborhood boundaries actually emerge in the data, and others don't. So in this picture, you see this area. This is the South Lake Union area. This is where Amazon is. This is almost the exact neighborhood boundary for the South Lake Union area, except for this little piece over here. And that area has a particularly distinct parking behavior because Amazon is there. So you tend to see people arrive in the morning and then be parked throughout the day and then leave in the evening. Similarly, this area over here, this is called Cherry Hill. There's a big hospital there. There's a bunch of medical facilities around that area. So you see a high penetration of disabled placard parkers. And these people don't pay for parking. So you actually see a really low paid space supply or paid space transactions in this area. So another thing, so what we're hoping is that, yeah, this can lead to better pricing schemes. So another thing we're looking at is just taking the block face utilization data and then applying Hodge decomposition ranking to identify sources and sinks in the data. So across the graph of the transportation network. So this is this Belltown area plus a little bit of this commercial core area, they call it. And so we applied this Hodge decomposition ranking to this, and we can identify these source nodes, which are the blue nodes, and these red nodes, which are the sink nodes. In this, so this is a heat map. Red is higher density of cars parked. Green is low density. And so this picture makes sense because one of the new pricing schemes that SDOT has implemented has made this area really expensive because there's people tend to park there, and then it causes congestion for through traffic. So they made this area a lot cheaper, and you can see that people sort of come into this area at these from these source nodes and then flow into this area where it's more red. So the next thing, so one of the interesting things that we can do with this is both sort of validate some of their existing pricing schemes and also help them decide where to do new ground truth studies. So that every year they decide to go out and pick a certain number of block faces and then count the cars on those block faces, and this is what they use to make decisions for the whole year. But by using this technique to identify sources, one of the things that we can do is have them do less studies, but more frequently throughout the year. So less studies, so usually they study every block. So one of the things we can do is say, okay, you only need to study a subset of the blocks to get an understanding of what the traffic or the parking density is going to look like in other areas, and you can do these more frequently throughout the year. And moving forward, I really like this particular application because we get to use some tools from algebraic topology. And the next thing we're going to look at is trying to apply some persistence of homology techniques to be able to extract out persistent structures as the topology of this network changes. Okay, so we talked about how you can integrate the user by taking data and then building user models, or building models of how users consume resources in these different infrastructure systems. But now I want to talk about how you can actually close the loop around the user. And so in this context, the value of information becomes important, both from the point of view of the user deciding to offer or allow or exchange data about its consumption or more high fidelity data in exchange for better quality services, and from the point of view of the infrastructure provider offering information to the user or deciding how much to spend on creating information structures that can then induce particular patterns of behavior in the users. So two things that we've looked at are the design of privacy-based service contracts and information schemes in urban parking. So again, Roy didn't talk about this, so I'm going to have to talk about it. So Roy did allude to the utility versus privacy trade-off, and so one of the studies we did, which he did show the plots of, compared how privacy, using our inferential or utility-based privacy metric, how privacy increases as you increase your sampling period, while on the other hand, your efficiency of your direct load control scheme decreases as you increase the sampling period. So that's a sort of intuitive response. So in this case, the motivating example is maybe you have some smart meter at your house. Your energy provider wants to do direct load control. So perhaps they use this disaggregation scheme to extract out the HVAC usage, and then they come up with a direct load control scheme that then is sent back to your house. So as I mentioned, the problem with this energy disaggregation problem is that it potentially exposes privacy risk. And so there's plenty of studies showing that this is the case. There's some studies showing, for instance, that you can infer when people are eating, not only what they're watching, or not only that they're watching TV, but what they're watching. And as Roy showed, we can infer things like your income level. And in addition, this information is really valuable to a number of different parties. Advertisers who want to sell you maybe appliances, law enforcement who wants to see if you're growing weed, criminals who maybe want to see if you're home so they can break into your house, and perhaps even the power company who wants to design incentives. So given the utility privacy trade-off that Roy talked about, our solution is sort of an economic solution. The solution is to balance this trade-off. And we take the point of view from designing or coming up with a scheme to trade off between utility and privacy from the point of view of the power company. So basically what we did is design service contracts that are differentiated by privacy. So consumers can self-select which contract they want based on their needs and wallet. And so the contract actually has either a sampling scheme or a privacy-preserving data collection scheme offered at a particular price. And so we can characterize these contracts in terms of things like the prior across the types. So the utility company doesn't necessarily know how the consumers value privacy. So it does have a prior across these types in the population. We can also characterize it in terms of the particular privacy metric that we choose and how much privacy loss there actually is. One of the things that we can show is that people who value privacy very highly, they end up free riding on the rest of society. And this is because they enjoy some information rent due to the fact that the power company doesn't know their type. So this sort of brings us to the conclusion that you possibly need regulation to come in and help realize the social optimum. In addition, we find that when there's privacy loss risk, there's an incentive for investing in insurance, so sort of hedging your bet, whether you're the utility company or the consumer. So we also looked at designing insurance contracts when you have risk-averse utility companies and consumers. And so one of the interesting impacts, I think, of this work, and it sort of exposes a direction for future research, is the fact that privacy risk motivates a study between security versus insurance investment. Okay, so switching gears to the transportation space. So on top of our learning framework, and I'm going to particularly talk about this weighted clustering scheme that we applied to the Seattle area, we imposed a framework in order to design feedback to the users. And so using the data that we got for each of the neighborhoods, all of the load data in these clusters, we extracted a model of a queue, and then we showed through simulation, which I am not showing you the results here, but you can just believe me if you like, that if we simulate these queues, then it actually matches the load profiles that we see in reality. So what we decided to do is then impose what's called a supermarket game on the system of parallel queues. And so a supermarket game is exactly what you think. You arrive to the supermarket, and based on information you have, observing how many people were in line, for instance, you decide which queue to get into. So in this context, you have a slightly different interpretation of the value of information. So in particular, the way that we look at it is as this expected reduction in expected waiting time due to a gain in information. So as I mentioned, you have drivers, potential parkers who are arriving to this set of queues, which represent the neighborhoods throughout Seattle. And they got to decide which queue to get into to park. And so some of the information, so there's three options. They can either pay to observe, and so this paying for observe doesn't mean they necessarily pay monetary value. It could be paying in terms of time, time to search, for instance, on your app that tells you where to park, or on Google Maps or something like that. The other option is to join without observing, so you do this blindly, or you can balk, so you can just choose to ride your bike or take the bus or park on off-street parking or something like this. And so the part of the population that actually joins the queue are these represented here with probability P(O) for the observing population and probability Pj for the non-observing population. And the observing population has information such as mean service time at each of these blocks, the arrival rate, for instance, or expected occupancy, maybe even the price. So there's actually some studies showing that some huge number of people who park in downtown areas aren't even aware of what the price is that they just paid for parking. So if you do have a dynamic pricing scheme, then potentially you're not even affecting the behavior of a huge part of the population. Okay, so this is just an example of calculating the Nash and what the effect is on the average wait time, which essentially tells us how people are circling through the city, and the block face utilization, which is the occupancy rate. So what we can do, so on the x-axis of all of these plots is the traffic intensity. So this is the ratio of the arrival rate to the queues to the number of queues, or sorry, the number of servers, which is the number of parking spaces, times the service rate, which is how long people park. So yeah, this is called the traffic intensity. And so as it goes towards 1, basically the arrival rate is approaching this number of servers times the service rate. So we can calculate the Nash equilibria of this game. So it's a symmetric equilibrium because we assume that all users are homogeneous. And what's interesting here is that the observing, for both, this is just empirical evidence, no real theoretical comment, but I think it's kind of interesting to note that the observing, in both the socially optimal case and the Nash case, the observing and the joining populations, or the portion of the population that observes and joins, tends to approach each other. That's what we see in these two green lines and these two purple lines. On the other hand, you see that the balking probability in the Nash case, people do not balk until the intensity gets almost close to 1. Whereas people balk very early on with low traffic intensities under the socially optimal solution. And so you can see the effect of that on the average wait time. Because people are not balking at high traffic intensities in the Nash case, you see that the average wait time increases really rapidly while the wait time for the socially optimal is low. Similarly, you see the utilization increases much faster than the utilization in the socially optimal case. Okay, so moving forward, the next thing that we're looking at is including more interesting behaviors, such as jockeying between the queues. So then it's not just a one-shot game of choosing a queue and joining a queue and staying in that queue until you find parking, but instead you could bounce between neighborhoods. And we're interested in selecting this information structure, so for instance, what information we provide them, or even the cost of information in some sense, in order to achieve the socially optimal outcome. Okay, so the third participant in this data market, and so this is almost a complete picture of what we're thinking about abstractly as the data market, are these aggregators. So they're just third-party companies who come in and provide services that the infrastructure system cannot provide. So examples might be this, for instance, this company C3. So it says C3 Energy up here, but they've now pivoted to be C3 IoT. And so one of their parts of their company is based on energy, and what they do is that they take and aggregate energy data from a bunch of different, or from service providers, and then offer them services such as theft detection or management of assets. Similarly, there's existing aggregators who provide information to the users, such as Waze, who provides a suggested traffic or suggested routes for traffic. So I'd like to talk about two things. First is this share. So these are going to be more open areas, less work that is either ongoing or previous. So I'm going to talk about this concept of the sharing economy and platform markets, and then open data initiatives and issues that arise around these open data initiatives. Okay, so an alternative way to think about the sharing economy is as a collection of platform markets. So these are essentially multi-sided markets in which you have an intermediary that captures the value of the interaction between different user groups. And you see these both in transportation and energy, so I put up some examples. Uber and Lyft are very specific examples of this, in which they're basically the multi-sided market maker, and they subsidize drivers by providing them a platform in which they can connect to riders. And then they benefit from the connection of these riders to drivers. And the reason, so this environment has been such that you could have these platform markets for a long time. However, the only reason that they're emerging so rapidly is because of CPS and IoT technologies. So this has caused a reduction in information costs and then made it profitable for them. So I think there's some interesting new challenges that we can think about in this context. First, because we're using these CPS and IoT devices, there are a number of privacy and security issues that we need to factor into the design of these multi-sided markets. Furthermore, they're not just a market to exchange even just data or basic services such as labor, like with Amazon's Mechanical Turk, but instead they're coupled with systems that have dynamics and physical constraints. Okay, so one of the problems that we're looking at is this issue of ride sharing. So we're trying to combine some tools from hybrid systems theory along with these queuing games to model these two-sided markets in which, for ride-sharing companies in which they use surge pricing. So when you have more passengers than drivers, you change modes to a higher surge price and vice versa. And so in this two-sided market, passengers can choose to pay a surge price or wait till the price drops, which means they have to wait until there's a change in the number of drivers versus passengers. Or they can just opt out, so take a different mode of transit. On the other hand, drivers can decide to participate or not, and which fares to accept. So one of the things that we're looking at is understanding the effect of these different thresholds that are used, for instance, by Uber, and the arrival rates, how frequently drivers arrive to the system and passengers arrive to the system, on the overall efficiency of the equilibrium of the game that results from this behavior. So the next thing that we're looking at is then how do you actually integrate mixed mode transit solutions. So I'm working with a company called Swiftly, and so there's a billion of these companies, but Swiftly is the one that somehow I got connected to. And so they present users with, so they aggregate all of the ride options that you have, so Uber, Scoot in San Francisco, the bus, walking, and they're presented to you on your cell phone, and then they show you like how many calories you're going to burn, like what is the cost of this, how long is it going to take you, and you select which one you want. Not only that, you can also order your preferences, and so they've been collecting all of this data, and their business model is that they're going to repackage this and sell either the data itself or the statistics to other companies such as Uber. So the problem that I want to look at is going beyond just this issue of trying to model the back and forth between passengers and drivers in the ride-sharing problem, but to look at what happens when urban constituents are choosing a path through the city by using both their car, the bus, and some of these ride-sharing companies or any other transit option. So maybe you go from your home, you decide, okay, I'm in a hurry, so I'm going to drive to a nearby bus station, I'm going to take the bus for a little while, and then I'm going to hop an Uber and get to work. And then maybe in the afternoon when you're ready to go home, you say, okay, I'm not in as big of a rush, so I'm just going to be a little more economical and take the bus back to where I parked my car and then go home. So what we'd like to do is say, given the two-sided market framework that I described before for these transportation network companies, plus bus schedules, among other things, along with the mixed mode choices that we get from Swiftly, and we want to build an inverse model of decision making. And so one of the factors that you have to consider is it's not just money and time that play a role, but also things like weather and individual's mood, and many other things. So one of the frameworks that we're thinking about using is something that we've applied in the context of energy, where we learn a mixture of utilities model. So this, for the example that I'll describe to you, we applied this in a game that we created in Crest over in Quarry Hall. So we had participants who sit in a particular area, vote on lighting preferences. They get the average of their lighting preference. So this is the dim level in the whole area. That gets implemented, and then people get points based on how energy efficient their vote is. So we took a model of their utility where the first term is how comfortable they are, and the second term, well, this psi represents how much, has a term about how we distribute the points to people. And so these parameters, theta, in some sense, will tell us how aggressive that person is, whether they're really not playing, they don't care about the money, for instance, or they're really aggressive and they mainly care about winning, they don't care about their lighting comfort. And so what we can do is, using the equilibrium conditions for our approximate Nash, we can build an identification framework in which we can learn the parameters of these utilities. And in this plot, I'm comparing this is a forecast of occupants' decisions, and on the y-axis, it's the average lighting votes. And so these black dots, which may be difficult to see, I'm not sure, it's kind of small, are the ground truth. This blue thing is if you just used ordinary least squares. The gray line is if you did basically eta boost with the ordinary least squares. And then the mixed utility learning framework outperforms all the other methods, which is this yellow one. So we're hoping to, one of the cool things about this framework, I think, is that not only do we get to learn the utilities of agents, but we can see how they're correlated. And so one of the things that we're looking at is how we can leverage this to form pseudo-correlations and then so basically player cost functions are now going to be a combination of their cost function plus all the people that they're correlated with or anti-correlated with. scaled by the correlation factor. And then we recompute or re-estimate the parameters of the utility given these pseudo-correlations. Okay. So what we'd like to do is extend this to the case where we have this multimodal or mixed mode transit solutions, given the data that we have from Swiftly. But we want to add an extra layer using some framework that is used frequently in economics and also in cognitive psychology, this loose Shepard choice rule, which is essentially a softmax over a sequencer, or a set of possible utilities. So in this context, theta will represent, for instance, an ordering of the preferences. So as I mentioned, you can order which modes of transit you typically like to take on the app. And then these different utilities will be the utility of the different modes that you can choose. Okay, so because I've been working with Swiftly among several other companies and even this Department of Transportation, I've noticed something very interesting. So one, cities are moving towards open data policies. So this means that every bit of data they collect, they have to provide to anybody who asks. It doesn't even have to be a citizen of the area. In addition, third-party companies are coming in and they're saying, okay, I can provide you the city services. I can collect data for you. I can act as a platform for you. And so some of the data that they're collecting through their technologies now has this issue of whether or not intellectual property will be exposed if they're making it available in this open data framework. So in addition, often these companies, like Swiftly, for instance, and C3, who I've talked to extensively about this, they want to share the data with researchers, but they don't know how because they're worried about their IP. So what we would like to do is generate mechanisms that deconflict these open data policies with intellectual property protection. So one of the things that I've been thinking about doing recently is considering a framework in which you can combine whatever statistic that you want to compute, let's say, with differential privacy guarantees in order to offer different data packages that cost different amounts of money and have different privacy guarantees. So for instance, maybe this top one, for instance, let's say, has very low privacy guarantees but cost a lot of money. And the reason that it might cost a lot of money, intuitively, is that the third-party service provider now has to take the risk of the privacy breach. So they might lose, for instance, intellectual property by offering this high-fidelity data. And you can imagine a graded set of options where the lower-priced one has greater privacy guarantees. Okay, so the last thing I want to talk about is the final piece of this data market structure, which is the regulator. So one of the things that we're noticing is that regulation is not keeping up with the technologies that we're using. So Uber is an example of this. So there's a number of complaints about them, for instance, encouraging their drivers to operate illegally and saying, oh, we'll pay your fines. Or, there's been a lot of pushback about the fact that they don't hire employees, they just hire contractors, and that this can be a labor issue. They're not the only ones. Airbnb is facing some of these same negative comments. And so one of the things I think that it's important for us to think about is how we can develop technologically aware regulation and policies. And so perhaps what this requires is for us to have better communication with those policy and regulation makers. Okay, that's it.